Okay, we're looking at adding vectors tip to tail. We're going to look at a general case here, and then in a minute we'll look at a numerical example, and I'll show you how to use the cosine law to solve such problems. So here we have vector u and vector v. And if we were to add the two of them together, vector u plus v is the vector we get when we take vector u and we follow it with vector v. So I'm going to put the tail from vector v at the tip of vector u. So that's v, that's u, and the resulting vector is the arrow that you get when you start at the tail of vector u and finish at the tip of vector v. So this vector here is equal to vector u plus v. What it really means is if you were to follow a path starting at the bottom of u, following u, and then following v, this is the equivalent path. It's simple enough without any numbers. I'm going to show you a numerical example now. So here we have, and we call this quadrant bearings. We have two vectors, 12 north 50 degrees east and 15 north 35 degrees west. And I would like to add the two of them together, so I'm going to need to know both the magnitude and the direction of the resultant vector. We call the vector that you get when you add two vectors the resultant vector. So first off, I'm going to just try and sketch them. So 12 north 50 degrees east. So a vector going north is going to look like that. And what this is saying is I start off north, and then I must rotate it 50 degrees towards the east. The east is this way, and that's about 45, so a little bit more. That's north 50 degrees east. Okay, that's my first vector. My second vector is 15 north 35 degrees west. So it's going to be a little bit longer than that one. And we start off going north, and we rotate about 35 degrees towards the west. I now want to add these two vectors together. So to add these two together, I'm going to take this one here. Remember, it has a magnitude that is 15. And its direction is 35 degrees west of north. So I can draw that in by drawing a coordinate here. And right here is where we're 35 degrees. So I'm just going to label that in here. So that's this vector, and I'm adding this one to it, so I'm going to put them tip to tail. But remember, this vector is north 50 degrees east. So I'm going to draw my coordinates in here. And I'm going to clearly label that this is 50 degrees right here. And again, here we have a magnitude of 12. So this is this vector here. The magnitude is 12, and we go north and rotate 50 degrees towards the east. This vector here has a magnitude of 15, and we go north and rotate 35 degrees towards the west. And I'm now going to put these two vectors tip to tail. Okay, so here's our vector 15 north 35 degrees west. This one is 12 north 50 degrees east. And I want to add the two of them together. Now, what I really need to know, I'm essentially putting together a triangle like this. And what I'm looking for is, first off, I'm looking for the magnitude of this side right here. Here we have a magnitude of 15, and here we have a magnitude of 12. I didn't do a very good job drawing that to scale. Let me shorten the 12 and lengthen the 15. Here we go. Now to figure out this magnitude, what I need to know is what angle do I have inside of here. To find this angle, I'm going to use this 35 degrees and this 50 degrees together to figure out everything that I can. If this is 35 degrees, right here is also going to be 35 degrees. We have a Z pattern, and since this line just runs north-south, and so does this one, we have parallel lines. So inside of our Z pattern, if this is 35, this angle in here must also be 35. We also have that this angle here is 50. If I was to go from here all the way around to here, that's 180 degrees. So the angle inside here, I'm calling that angle A. That angle A is the same as this angle A here. And that angle A is going to be 180 degrees minus 50 minus 15. So that angle A is 180 minus 50, because I'm taking away this part, and minus 15 because I'm taking away this part. Did I say 15? I apologize. Minus 35. This angle here is 35. This angle here is also 35. So minus that 35. So what's left over is going to be 95. So angle A is equal to 95. That's this angle in here. And what that means is I can find this unknown side here, and I'm going to call the resultant vector vector r. And I can find this here, its magnitude, by using the cosine law. So according to the cosine law, the magnitude of r is going to be equal to the square root of 12 squared plus 15 squared minus 2 times 12 times 15 times the cosine of 95 degrees. And remember, this is 12 squared, not 12, and that's 15 squared, not 15. So again, this is just the cosine law. This side length here, that's the magnitude of this vector that we're looking for, is going to be this squared plus this squared minus 2 times this magnitude times this one times the cosine of the angle in between them, which is 95 degrees. So that makes this magnitude so we have 12 squared plus 15 squared minus 2 times 12 times 15 times the cosine of 95 degrees. Okay, so what we're interested in is the square root of 12 squared plus 15 squared minus 2 times 12 times 15 times the cosine of 95. And that's equal to 400.376. And we now want to take the square root of that. And the square root of that is 20. So our magnitude here is equal to 20. That makes r equal to 20. And the only thing that's missing now is the angle. And we need to know what angle it is from north. You can clearly see that our resultant vector, when we put them tip to tail, is going to be upward. So it's going to be north, and then we just have to figure out what angle is going to go in here. If it was exactly north, this would show up as 35 degrees. So what we're interested in knowing right now is this angle here. I'm going to call that angle B. And to find this angle, because we have this angle, this side, we can use the sine law. So according to the sine law, the sine of B divided by 12 is equal to the sine of A divided by 20. So that's going to be the sine of 95 divided by 20. So the sine of B is going to be equal to 12 times the sine of 95 over 20. So we take 12 times the sine of 95 and we divide that by 20. That's the sine of B. So we're now going to inverse sine. And we find that angle B is 36.7. Okay, now watch closely. This is 35, but this angle here is 36.7. Let me redraw that for you. So right here, that was one of the vectors we were adding, and this is the resultant vector. The angle inside of here is 36.7. But if I was to draw in a true north compass point, I get an angle right here of 35. That means that this tiny angle right inside of here must be 36.7 minus 35. That makes this angle that I'm looking for 1.7. So the 35 plus 1.7 gives us 36.7. So my final answer, when I'm adding these two vectors, is going to be that it's equal to a magnitude of 20 at a direction north, 1.7 degrees east. Now, if this angle came out less than 35 degrees, I would know that I was north and I would have to rotate towards the west. You have to carefully draw your diagram and closely look at it each time. The diagrams, I'm warning you, do get a little bit messy because you're putting a lot of information on them. You have to include the full compass point around the tail of each of your vectors as you do these. But ultimately, you're creating a triangle, and in that triangle, the two vectors you're adding together are tip to tail, and you're finding the magnitude and the direction of the third length of that triangle.